Dear students, welcome to the online class. I am Dr. S.S.C. Hiremat. In this video, you are going to study about the partial molal properties or the partial molal quantities. Suppose X is a thermodynamic function or that is function or a property such as internal energy, enthalpy, Helmholtz free energy, Gibbs free energy, volume, entropy, etc. Okay. Then for a closed system, temperature, pressure, volume are the variables but independent variables are only two, that is temperature, pressure, or temperature, volume, etc. Okay, then we can write X is the function of temperature and pressure. Okay, X is the function of temperature and pressure, or X is the function of temperature and volume, etc. Okay, this is for closed system. Then for open system, independent variables are that is temperature, pressure, or temperature and volume, only two are taken. Then number of moles of component 1, number of moles of component 2, and number of moles of component I. Okay, these are the variables. Then we can write X is the function of temperature, pressure, N1, N2, so on, Ni. Okay, thus the thermodynamic function X is the function of temperature, pressure, number of moles of the components present in that, where N1, N2, Ni are the number of moles of component 1, 2, okay, and I, etc. Components 1, 2, 3, 4 up to I, etc. Okay. Now on differentiation of this, we can differentiate this X partially with respect to all the variables. On partial differentiation of X, of X, we get, that is dx is equal to dou x divided by dou t, partially differentiation with respect to temperature, at a constant pressure N1, N2 up to Ni, and this is dt. Okay, plus now you keep others constant, differentiate with respect to P. Then dou P, that is dou x divided by dou P at a constant pressure N1, N2 up to Ni, then this is dP. Plus similarly dou x divided by dou N1, differentiate with respect to 1. Okay, that is dP plus at constant temperature, pressure N2 and so on, Ni, and this is dN1, and so on. Lastly, we may get the other one. Okay, so on, plus dou x divided by dou Ni at the constant temperature, pressure N1, N2, and this is dou dNi. Suppose this is equation 2. Let us number this equation 2, this as equation 1. Okay. Now, these are the partially differentiated data. Okay, this, etc. Here, the change in free energy or change in. Now, in equation 2, this dou x divided by dou N1 at a constant, this dou x divided by dou N2 at a constant, these variables, these are known as partial molar quantities. Okay, then we can write the partial molar quantities separately such that is dou x divided by dou N1 at a constant temperature, pressure N2 up to Ni, it is the partial molar quantity of component 1. Okay, it is represented by x1 bar. 1 indicates the number of component, the component number. This is partial molar quantity or property of component 1. This is component 1 for this. Okay, similarly we can write that is d dou x divided by dou N2 at constant temperature, pressure N1 up to Ni. This is represented as x2 bar. This is nothing but the partial molar property of component 2. Thus, generally, we can write for the ith component, that is dou x divided by dou Ni at constant temperature, pressure N1, N2. Okay, this is represented as xi bar, that is partial molar property of component 3, component I. This is component I. Okay, in this way, the partial molar quantities for different components can be represented symbolically in this way. Now about all other components. Here x is a function or a property. Now if we take the other thermodynamic functions such as internal energy, enthalpy, etc., we are going to get the different values. Okay. Now suppose x is our internal energy. Okay. Then we may write d E divided by dou 1 at constant temperature, pressure Okay, Ni, let us take it as Ni. This is N1, N2, etc. This is represented as the Ei bar. Ei bar. Okay, this is nothing but the partial molar internal energy, partial molar internal energy of component 1, that is I. We are using here the I, component I. Okay, similarly for enthalpy we may write dou H divided by dou Ni at a constant temperature, pressure N1, N2. This is represented as, that is dou, that is H bar I, ith component. Partial molar enthalpy of component I. Okay, similarly we can write it for the dou A divided by dou Ni at a constant temperature N1, N2, etc. We may write it as the A bar. Okay, this is Ei bar, that is partial molar Helmholtz free energy of component I. Okay, then about free energy, Gibbs free energy, dou G divided by dou Ni at a constant temperature N1, N2, etc. This is Gi bar. Okay, Gi bar. Okay, this is partial molar Gibbs free energy of component I. Okay, but here in this case this is represented with special symbol, that is mu I, and it is also called the chemical potential. Okay, chemical potential of component I. Okay, means in this case, in the partial molar free energy change, we are using the symbol, that is mu I, that is also called the chemical potential. Okay, then similarly we can use, that is dou V divided by dou Ni at a constant temperature, pressure N1, etc. This is represented as Vi, that is partial molar volume of component I. Okay, in this way for each thermodynamic function we are going to use one symbol. Okay, that is A bar I, H bar I, etc. Okay, now let us study about this thing. That is, the partial molar property of component 1 is defined as the change in that property when 1 mole of that component is added to such a large system that there is no change in the composition of the system. Okay, this N2, N3, N3, etc. their concentration remains the same. Okay, thus we define the partial molar property as the change in free energy when 1 mole of that is component is added to such a large system that there is no change in the concentration of the other components. Okay, now by substituting the symbols in the equation 2, we get that is dou x, that is dx that is equation 2 is nothing but dou x divided by dou T at a constant pressure N1, N2 etc. and dt plus dou x divided by dou P at a constant temperature N1, N2 and so on, that is dP, plus and the dx divided by dou x divided by dou n is substituted by its symbol in this way. We are going to get this is x1 bar into dn1 plus for the second x2 bar dn2. For the ith we are going to get xi bar divided by dni. Okay, dni. Now, and the temperature and pressure are kept constant. That equation becomes, that is dx when temperature and pressure are constant. When temperature and pressure are constant. Then when temperature is constant, this becomes 0, then totally this term becomes 0. And pressure is kept constant, this becomes 0, then totally this becomes 0. Then constant, suppose this is equation 3, equation 3 becomes that is equal to dx. What we have kept here? We have kept the temperature and pressure are constant. Thus we have to write temperature and pressure are kept constant. These terms disappear. Then we may write x1 bar dn1 plus x2 bar dn2 and so on, xi bar dni. Suppose this is equation 4. In this way, any thermodynamic function may be represented in the form of the symbol as I have already shown them. By substituting them, we are going to get the general equation for this. Now, the next thing is about partial molar Gibbs free energy. Partial molar Gibbs free energy. That is partial molar Gibbs free energy. Partial molar Gibbs free energy. Okay, and it is represented as Gi bar. This is also known as the chemical potential. That is chemical potential. Okay, chemical potential, it is represented by mu I for the ith component mu I. Okay, then we can write the expression for this, that is partial molar Gibbs free energy. Suppose this is dou G divided by dou N1, okay, at constant temperature, pressure and 1 is used here, or let us use the I, then N1, N2 etc. are kept constant. Okay, this is represented as G1 bar, or this is mu1, that is mu I. I am using the I, mu I. This is chemical potential. Okay, mu is the chemical potential. Then you define the chemical potential or the partial molar gives free energy. Thus, the partial molar gives free energy change, that is the chemical potential, is defined as the change in free energy when 1 mole of the ith component is added to such a large system that there is no change in the concentrations of the other components. Okay, in this way we can define. And another way of defining the chemical potential or the molar gives free energy is that here if we take this is infinitesimally small, that is d dou n1 as a dn1. In that way also we can define. That is partial molar gives free energy, that is chemical potential is defined as the ratio of change in free energy to the change in number of moles of ith component. Okay, when the concentrations of, that is when the infinitesimally small amount of the component I is added to a system. Okay, this is 1 mole, 2 mole, etc. It means we may define it as the ratio when this is infinitesimally small amount. Infinitesimally small amount. Thus, the chemical potential is defined as the change ratio of change in free energy to the change in number of moles when infinitesimally small amount of that component is added to the system when other concentrations of other components are constant or large enough. Okay, this is also one equation, that is 4 and 5. Okay, by substituting the values of m, the equation 4 becomes, by substituting the values of mu I in equation 4, we get that is d g equal to, okay, we want to write this for the Gibbs free energy, g, and when temperature and pressure are kept constant, we are using here, this is equal to, okay, mu 1 d n1 plus mu 2 d n2 and so on up to mu I d n I. Okay, this is the expression for the total change in the free energy when the number of moles of the components as shown in this equation are added to the system. Okay, this is the total change in the free energy. This is the chemical potential or the free energy change due to first component. This is for second component and ith component. In this way we can write this is the total free energy change of the system. Then variation of chemical potential. Variation of chemical potential. Variation of chemical potential. Chemical potential with pressure. With pressure. Variation of chemical potential with pressure. And we have defined here, that is chemical potential is defined as, that is dou G divided by dou N1. Suppose this is for one component when temperature and pressure are kept constant. Okay, on differentiation with respect to pressure, on differentiation with respect to pressure, what we get, that is dou mu1 divided by dou P is equal to, at constant temperature, this is equal to dou G is already there, we want to differentiate this with respect to pressure. Then dou square, then dou P and dou N1 already there. Okay, suppose this is equation 6. This is equation 6. Now, from the combined equation of first and second law, we know that is dg equal to, from combined equation of first and second law, we get that is dg equal to v dp minus s dt, v dp minus s dt. At constant temperature, okay, it is with pressure at a constant temperature. What we get? We get that is dou G divided by dou P at constant temperature equal to V. Constant temperature, that is equal to V. On differentiation with N, on differentiation with N1, okay, with N1, we get, that is, we get, it is right here, differentiate this with respect to N1, that is dou G is already there, dou square G, and differentiate with respect to N1, and dou P is already there, that is dou P is already there. Okay, then differentiate this also with respect to N, that is nothing but dou V divided by dou N1, dou V divided by dou N1. Okay, then this is equation 6 and this is equation 7. That is, equation right hand side of equation 6 is equal to left hand side of equation 7. Then equating equation 6 and 7. Okay, equating equation 6 and 7, we get dou mu 1 divided by dou P is equal to dou P at constant temperature equal to dou V divided by dou N1 at constant temperature, pressure, okay, and N1 etc. This is nothing but V1 bar. It shows that change in chemical potential with respect to pressure is nothing but the partial molal volume of that component. Okay, partial molal volume of that component. Then we can also write the variation of chemical potential with temperature. Okay, now mu1 equal to this, let us derive that also. Okay, then mu1 equal to this. Then on differentiation with respect to temperature, we get dou mu1 divided by dou T at a constant pressure equal to dou G divided by, we want to differentiate this with respect to T, that is dou T, this becomes 2, and dou N1. Okay, dou N1. Now we will number this equation as 8. Now from the combined equation of the second law of thermodynamics, we know dg equal to v dp minus s dt, v dp minus s dt. At constant pressure, at constant pressure. This equation becomes dg equal to minus s dt. Then that becomes dou g divided by dou t at constant pressure is equal to minus s, that is entropy, minus s entropy. On differentiation with respect to n1, we get d square g divided by dou n1. Okay, differentiate this with dou n1 and dou t. This is nothing but minus dou s divided by dou n1. This is nothing but s minus s1 bar. Okay, then equation 8 and 9. Left hand sides are same, that is one sides are same, d square g divided by this, d square g divided by this. Then equating equations 8 and 9, equations 8 and 9, what we get? This d mu divided by dou mu divided by dou t at a constant pressure. This equal to this, this equal to this, this equal to this. That is minus s1 bar. Suppose this is equation 10. What it shows? The variation of chemical potential with the temperature at a constant pressure is nothing but the negative partial molal entropy. Then variation of, for ideal gas, we have ideal gas equation, that is PV equal to RT. For n mole, the equation becomes PV equal to nRT. If it contains more than one component, then the equation becomes PV equal to RT into N1 plus N2 plus N3 up to Ni. Okay, if it contains more than one components, then we get equation P equal to RT divided by P into N1 plus N2 and so on up to Ni. Okay, on differentiation with n1 one component, we get dou P divided by dou n1 when temperature and pressure are constant, yet constant pressure and temperature. Okay, at a constant temperature and pressure. Constant temperature and pressure, we get Tp equal to RT divided by P. Then on differentiation of P with respect to N1, we get dou V divided by dou N1. This is on difference RT, P are kept constant, they remain as it is. When N1 is differentiated with N1, we are going to get 1. When N2 is differentiated by N1, 0, 0, all terms becomes 0, then we are going to get only this. This is nothing but V1 bar. Thus, the from equation, that is above equation, suppose this is equation 11, from above equation we get, what we get? D mu I divided by dP is equal to is equal to, that is P1 bar. This is equal to RT divided by P. RT divided by P. That is equation 12. Next, variation of chemical potential with pressure. It is nothing but the partial molar volume, which is equal to RT divided by P. Now about the significance of chemical potential. First one, according to the definition, mu1, that is dG equal to dou N1 at constant temperature, pressure, N, etc. Here it shows the increase in free energy by addition of the one component here. Thus, the chemical potential gives the increase or the change in the free energy on addition of a component. It gives the increase in free energy, on addition of one component. Okay. Thus, the chemical potential is nothing but the increase or the change in the free energy on addition of one component. Then second one, it is independent of mass. Means chemical potential is independent of the mass. It is an intensive property. That is, it is an intensive property. It is an intensive property. Independent of the mass means it is an intensive property. Third one, matter flows from a region at higher chemical potential to the region at lower chemical potential. Matter flows from a region of higher chemical potential to the region of lower chemical potential, to the region of lower chemical potential. And another one is the chemical potential is an escaping tendency of that material. It is an escaping tendency of the component. Okay, of the component. Then fifth one is about it is nothing but the chemical potential is nothing but the free energy per mole. Okay, thus it is nothing but Q for pure compounds. Okay, for pure compounds. For pure compounds or the systems, matters, this is chemical potential is nothing but per number of moles. That is, chemical potential is the ratio of free energy to the number of moles. That is free energy per mole. These are some significance of the chemical potentials. Okay, that is D divided by N. That is, N is the number of moles for pure substances.